Is your Dropbox folder local or an online folder?
Online as well.
No, but this one back here.
All my Dropbox is online. How come?
It's like Google Drive.
Yeah.
Because you can download.
Yeah, I know. But I'm little bit impressed by the speed.
No, there's a local copy as well.
Yeah, that's what I was asking.
Ah, yeah, I think the version on the Android phone is not, there's no local copies of the files. Because I got it on my phone, and I'm like, great, and then I noticed, oh wait, hang on, it's downloading every time I open something. Like, life is short. I won't use this. Okay, continuing now. So, oh come on, Lee.
Have you ever planned to upgrade your phone?
One day, maybe. But I like my phone.
You can have two. One for the Dublin bus. No.
Yeah. I like my phone. Huh?
Phone, close your ears.
What? Are you being dirty?
No. I'm being, as you call it, a pimp.
There's children in the class now behind you, so I haven't. Most of the time I don't know what he's talking about. Right, so what we're going to have a look at, we learned how to differentiate something like, we'll get to the title in a moment. Well, where have you been, Omar? Yeah, but where have you been? Yesterday? Yeah? Okay. Any special reason?
Very special.
That is special. What exam? IELTS?
SAT.
SAT? You're doing that? Alright. X squared. Derivative of x squared? Hey. Derivative of x squared? Guys, derivative of x squared 2x. Now, it might seem like we should be able to differentiate something like y squared, and maybe we think the answer is 2y.
Wrong.
But it's not. Of course not, because then the lesson will be over quite quickly. So let's see why that's wrong. So let's take a simple example. Let's say something like y equals x cubed. So y squared would equal x6. So if we differentiate y squared, we think we get 2y. That's what we're thinking we might get. And if we differentiate x6, we get 6x5. This makes y equal to 3x5, which is totally wrong, because y was x cubed. So when y squared differentiates, it doesn't differentiate like this. It's not as the same as x squared. So how do we differentiate a y term? Well, that's
like a product rule.
kind of like a product rule, but not product rule, more like a chain rule, which I'll show you now. And this is called, which is the lesson, implicit derivatives is what we need. So let's have a look. So suppose I have some function of y. In the previous example it was y squared, but whatever it is. And I want the derivative. The reason it doesn't work is, can anyone see why this is a problem?
Because it's y.
Yeah, because it's y and this is an x. Yeah. But you could do a little bit of a change here. You could say dy which is 1, df dx. So I've just multiplied by 1. Why is that useful? Well, I can swap the bottom two because I'm only multiplying, so I can just change them around. So I end up with dy dx df of y dy, which in other words is dy dx times f derivative, or basically it's f derivative times dy dx. So simply put, when you want to differentiate a function of y, you differentiate it as normal, but what's different is you multiply your answer by dy dx. So we can see this working correctly now. Let's go back to our example we had a moment ago. Y equals, what was it, x cubed? And I had y squared equals x6.
How does the f of y on dy turn into derivative?
I have no idea what you're asking me. Because this is derivative of f, the f dy,
Yes.
and this is f derivative. It's the same thing.
Yeah, and then why are we doing all this?
What do you, I don't understand. Be more precise. What are you talking about?
Why do we multiply by dy over dy? Which is like 1. Why do we multiply by 1?
Because I want to get a dy in here,
Yeah.
so I can swap it and have a dx and a dy. Because I'm trying to get a dy in this, because I don't want a dx in it. The dx is no good because I'm dealing with y. I need a way to introduce a dy. The easiest way, yeah?
But isn't dy over dx the derivative of?
No, because the function was f. Fy is definitely not the same thing as y. This is a function, like here, x cubed is our function, x cubed is our y,
Yeah.
and y squared is our function of y.
Oh.
And they're obviously different things, one's a square and one's a cube. Okay, so let's see this formula working correctly. So according to my formula, if I differentiate y squared, all I do is multiply by dy dx. So what's the derivative of y squared? That would be 2y dy dx. And derivative of x6? 6x5. Now let's test if that works. Let's go back here. Y equals x cubed. What does dy dx equal? 3x squared. Right? Let's see, what do I want now? Yeah, okay. So let's see, does 2 multiply y multiplied by dy dx make 6x5? 2 multiply y multiply dy dx.
2 multiplied by y.
Yeah, and y is x cubed. That's 6x5. So unlike the example earlier, it does actually work. It matches up just fine. You don't do the questions like this. I'm just doing it this way to show you it works. But what usually happens is you have problems like this. Y squared plus x squared equals 1. And I want the derivative. So if you wanted to, you could rearrange it and end up with some equation like this. But that doesn't always work. And in fact, that's not always possible. It's possible in this example, but it's usually not always possible, because this is a simple example. So this is where implicit derivatives become very useful, because what you can do is just differentiate everything. You don't have to rearrange anything. So derivative of y squared, 2y dy dx, yeah, plus 2x equals derivative of 1, 0. So now you can rearrange and get your answer. Dy dx equals minus x over y. If you were to rearrange this and do it the way we have been doing these types of problems, you will get the same answer, but it's longer, it's harder.
Okay, derivative of dy dx, which one is it? Is it the derivative of x squared?
Which one?
And
This
2y multiplied.
It's the derivative of this.
Yeah, but then the dy dx part,
Yeah?
it's the derivative of x.
No, the derivative of y.
This is the 2y, the derivative of. Like, where did you get the?
Take a moment and form a sentence, then ask me your question. I'll be drinking a coffee.
Well, what does dy dx equal to?
X over y.
That's the
But-
derivation of the whole.
Yeah, but at this point in the question, at this point in the question, we don't actually know what dy dx is. That's the point. We're trying to figure out what dy dx is. We only know what it is at the end here.
Oh, and then we kind of make it the subject.
Yeah.
Yes, we're making it the subject, yeah, correct, yeah. Let's have a look at one that's a little bit harder, okay? Let's say something like x squared plus xy plus y squared equals, again, we'll say 1. Okay, we're looking for dy dx, the derivative. Derivative of x squared? 2x. Be careful here, because this is a product. You need the product rule here, because it's x times y.
0 times
So, yeah, derivative of x
1
times y plus, and derivative of y?
dy over dx.
Yeah, 1 dy dx, or just dy dx, plus 2y
dy dx.
dy dx equals 0.
1, 0.
Are you a computer program now? So, rearranging here, x plus 2y dy dx equals minus 2x minus y. So dy over dx would equal minus 2x minus y over x plus 2y. So this is the derivative here. I have a couple of more examples to do, but I just want to give you one to try. Can I?
Well, can you just give us the formula?
There is no formula, really. It's a rule. When you differentiate a function of y, you multiply your result by dy dx. This is like the rule. I don't know, have anybody studied this before, or is this a
Yes.
new thing? You've seen it before? Lee? New or old? Oh, I'm teaching you something new. Exciting. And are you making notes? Even though it's something new and you haven't seen it before? That's it.
The notes should take it. It doesn't do the notes.
Okay. Can I give you one now to try? Go on. Yes. X cubed plus x squared y squared plus y cubed equals 3. And my question is, we'll do multi-parts. Part A. Find dy over dx. B. Find dy over dx at the point 1, 1. C. Find the tangent lines equation. Find the tangent at 1, 1. Part B and C are pretty short once you have part A done. So give this a try, and I'll do it now in a minute. Easy. Finished? Anyone else?
Yeah, so good. Continue.
Yeah,
This one.
can I make, take this?
You can't
Finish
take
it?
this way because that's wrong. You forgot to do.
Let's have a look at it now.
Square y square.
So, derivative of x cubed
This is right.
is 3x squared.
That's
And then x squared, y squared needs the product rule. So that would be 2x y squared plus x squared 2y dy dx plus 3y squared dy dx equals 0. So that's x squared times 2y plus 3y squared dy dx equals minus 3x squared minus 2xy squared. So dy over dx equals minus 3x squared minus 2xy squared over 2x squared y plus 3y squared. Did you get that?
Yep.
Now, for part B, I just want the value when x is 1 and y is 1. So this will be minus 3 minus 2 over 2 plus 3. So that's minus 5 over 5, which is minus 1. And finally, I want the tangent line, which is y equals mx plus c. Y equals minus x plus c. I used the point 1, 1 to get the c, so c is clearly 2. And I finish with y equals minus x plus 2.
Oh. I just wrote m equals minus 1. I didn't write the equation of the tangent. So didn't say the equation.
I did say it, I just didn't write it. And I said find the tangent.
Yeah, so
So,
doesn't mean equation.
true, it doesn't. But the context would suggest it does.
And don't confuse yourself. Write all the steps.
Do you need to write this down, yeah?
So the question, where did the 2 in the bracket come from?
Which in the bracket? This one?
Yeah.
Let's see, where did it come from?
It's,
It was here.
why is it x squared?
It was that 2.
That's the product.
I used the product rule, yeah, to this middle piece here. That is the
The product.
where is it gone?
X square y
Yeah.
square.
It was the derivative of x squared y squared, yeah.
Yes,
So
what's,
product rule, yeah.
what brings us in front of the x?
Oh, because it's multiplied, so the order doesn't matter. So I prefer to write numbers in the front. I just swapped x squared and 2 to make
So you
2 x
didn't
squared.
derive anything?
Nothing special really happened here to here, except for me putting the 2 in front and factoring the dy dx out.
Oh, it's just to clarify it in my head,
Yeah.
it's the same thing as x squared 2y.
Yes,
it
the
is.
same.
Okay, do you have that? Yeah. Can I continue?
dy dx is the gradient.
Yes. Continue?
If you wish.
I do. But may I? May I? May I?
That's
Everyone thinks so, except for this guy, Andrew.
There's almost
I really should continue, but I'm too tired to continue, so I'll allow him.
Do we have 2 lessons?
Take your time, Andrew.
Yes, okay. Now, another use of implicit differentiation is you can differentiate things that we weren't able to so far. I'll give you a good example. This was actually an exam question a little bit ago. The derivative of tan inverse x. Now, if you think about it, we know what the derivative of tan is. It's 1 over cos squared x. But tan inverse is actually not something we know how to differentiate. And before anyone says it, please, nobody give me the stupid answer saying, but teacher, why can't we just change this into 1 over tan x? I know somebody here was thinking that, and shame on you for thinking it. Because tan inverse x is not 1 over tan x. It's a different function which the Americans call arctan. It's the reverse of tan, the anti-tan, if you will. It's not 1 over tan.
Can we change
Were
it
you one
to-
of those people that are going to ask?
No, I wanted to ask, can we change it to tan y equals x?
This is the technique. So what we do, we cannot differentiate tan inverse, but we can differentiate tan. So the trick is we put tan on both sides. So we have tan y equals tan inverse x. But what happens on the right there?
Tan.
They cancel, don't they? So you're left with tan y equals x. Now we can differentiate. This is 1 over cos squared y times dy dx equals
0.
1. So what does dy dx equal?
1 minus 1.
1 cos squared y.
1 cos squared y. You're multiplying. So it's equal to cos squared y. Or in other words, cos y squared. Now that's not actually finished because you don't have, or you shouldn't have y in the answer. You want really to have x in the answer. You're looking for a function of x. So the trick here is, what is the definition of tan? It's what over what?
Tan over cos.
And the other one with the opposite adjacent and hypotenuse?
So that's opposite over adjacent.
Yeah.
Opposite over adjacent. Yes, that's right. So tan y is equal to x, or if you prefer, tan y is equal to x over 1. So in the triangle that has y as the angle, the tan of y is equal to x over 1. So the hypotenuse is square root 1 plus x squared. Now we can get the cos of y, because the cos of y will be 1 over the square root here.
Very complication.
Very complicated indeed, but very interesting indeed. Squared. So now we finish with 1 over 1 plus x squared as the answer. So the end of the story is the derivative of tan inverse. Where's my colours gone? Come on. The derivative of tan inverse x is 1 over 1 plus x squared. I have seen them ask this question in the exam. They said, show that the derivative of tan inverse is that.
I have a question.
Yes? Is it good?
No,
Okay.
I don't think so. It's like something to do with it.
Go on, go on.
Can we change tan inverse to, like, is the inverse to the power of -1?
Go on.
Is that what it means?
And what's power minus 1?
1 over tan.
He said the
And
beginning.
please tell me why I shouldn't come over there and slap you. Because what was the very first thing I said?
Yeah, no, I know.
No, what was the very first thing I said?
I know what you
Yeah.
said, but you were like, but what if we make it 1 over tan, and then we differentiate the denominator?
Am I on TV? Are you like trying to troll me or something? I said at the very beginning, this is definitely not 1 over tan. I said, don't make it 1 over tan, it's not 1 over tan. Thinking it's 1 over tan, and it's not. What did I say it is? What is tan inverse?
Arctan.
Arctan, it's the anti-tan, it's the opposite of tan, it's the backwards tan. It is not a 1 over tan. It's an entirely different function, and its only relationship to tan is that it reverses tan, but it is not 1 over tan. It's equivalent to saying you have x squared, and the reverse of x squared is square root x. Agreed? But you would never say 1 over x squared is the same thing as square root x, because it is not, obviously. Likewise, what is the reverse of ex? Log x. But you would never say 1 over ex is log x.
I have a question.
If you're going to ask me if this is 1 over tan, I will throw you out that window. Go on.
Can we use the chain rule for cos square y to differentiate instead of showing
We
the
can, but it doesn't really solve anything, because the problem is
the y?
the y. And anyways,
So
there is no differentiation to do after you get to this step.
Yeah, so there isn't any way to not get the trigonometry involved? The triangle cos?
Yes, there isn't any way.
Are you very sincere with your answer? Or
No,
are you
I'm lying a little bit, because there is a way. But it requires something that we haven't done yet, and it's kind of a stupid way. And for some reason, most of the students did it this way, and I can't understand how they all figured this way of doing it when I never showed them this way before the exam. But it seems like on the day when this question came up, all the students said, I'm going to do it this way, which I never showed them. Kind of a stupid way, kind of works, and I don't like it.
Can we know it?
No. Because it worked for this one, but it might not work for the one that you get. And I don't know which one you get if you do get one of these. It's better to do these sine, cos, and tan inverses by using the triangle. And we will study further trigonometry later, so we'll be doing more trigonometry anyway.
Is it sine? Or sine y?
Are you eyes on this?
Sine y?
No. No. I'm going to give you one to try now. Y equals 2 power x, and I want the derivative. And it's the same trick. I'll give you the hint. Hint, yeah, change it by using log, or more precisely log base e.
I really don't like using triangles.
Were you like beaten up by a bunch of triangles after school one day? Like, what have you got against triangles?
I want to know the other way.
When we get to the chapter, I will show you, if you're good. But I can't show you right now because it needs something we haven't done yet.
What's it called?
Differential equations. This one does not require a triangle.
Yes.
No.
Why ln2?
Give it to me with x only. I don't want y in the answer. Give me only x. No.
We can't have y in our answers?
I don't want y in the answer, and you can get y out of the answer.
Can we just substitute 2 to the power of x into it?
What's y equal to? That's right, Faisal. You've just been punked. Okay, you got it, yeah? Very good. So, we put log on both sides. So we have log y equals log 2 power x. I know I can't see right now. So we get log y equals x log 2. I'm doing all right. Derivative of log y is 1 over y dy dx equals, there we go. Derivative of x log 2?
X. Log 2.
Log 2. So dy dx equals y log 2. But what does y equal? 2 power x log 2 is the answer.
And the exam, we're not allowed to leave it as y ln2?
Correct. Have a look at what I wrote and then ask me your question.
Can you change the colors of your marker?
Yes.
Choices?
Yes. I just have these ones saved in my quick wheel.
Okay. Can you change them?
Yeah. What button does it? Not C, not B. I can't remember. There's some shortcut to open up the colours. Okay.
Because sometimes I don't see any difference in the color. I can see a blue and a not blue. That's what I see.
Okay, I'll keep that in mind when I'm writing. But if I want something really highlighted, I should use blue.
Or different colors. Green,
It's blue and red.
orange.
What's blue and red?
Like what you use.
Oh, I got black, blue, red, green, grey.
You've never used the green before.
No.
Yeah, oh, that's for special occasions. It's gonna have to be something really important to get the grey out. Okay, you got this? What's the problem, Fuan?
Why is ln2?
Here? Which line? 1, 2, 3, 4.
From 3 to 4.
From 3 to 4, okay. X log 2 is like a number times x. A constant times x. What's the derivative of kx? What's the derivative of 2x? What's the derivative of kx? What's the derivative of log 2x?
But I thought if...
Log 2 is a number. No, not product. Log 2 is a number. Tough break. Okay, you got this? Not yet.
But then you did derive.
I derive log y. Yeah, log y is 1 over y dy dx. Yeah. This was also an exam question one year, I remember. It's a bit of a pain because they won't say in the question what rules you need. You know, they won't say use product rule, use quotient rule, use chain rule, use implicit derivatives. They won't say that. Unfortunately, you need to figure it out yourself.
They give us the rules in the product and quotient rule.
Yeah, but the problem is not using the rules. I think the problem with students is knowing when and how to use the rule. Okay, can I continue? So if I look here, now just so you know, oh come on. Yeah. Question 1 is only for the science students, which is none of you. Question 2 and 3, and then the rest. 2 to 11 are, typical exam questions. Number 12, what's special about number 12 is they all require you to use some inverse function, a reverse function. Like for example, in A, B and C, you have to use log, like I did in my example. And then in D, E and F, you're going to have to use sine, cos and tan and a triangle. The most common type of question in the exam though are the ones from in the middle, 2 to 11. Okay. So I'd like you to do these for a few minutes, please.
From 3 to 10?
No, whatever ones you want. I wasn't saying, just don't do number 1.
Question 3.
Yeah?
Dx over dy, so there isn't, so like the first
dx over dy, that's me being sneaky. It's just 1 over, dy over dx.
Or make x the subject.
That's not what I was wanting you to do. True, but I just want you to proceed as normal and then flip the answer at the end.
Okay.
Okay?